as has been the case for all types of convergences, sequences, limits, sequences of functions, this definition only really works if you know what the limit is going to be beforehand. Well, we have the equivalent of Cauchy properties for sequences of functions as well. A Cauchy criterion for uniform convergence of sequences. So we have a sequence of functions fn going from a to r for every n, then fn converges uniformly to some function f on a0a, even if we do not know specifically what f is going to be. This is a theorem that shows the existence of a limit, but doesn't display the limit. If and only if, for every epsilon greater than 0, you can find a k epsilon in n. And here, let me re-emphasize no dependence on x, only on epsilon, such that the distance between fn at x and fm at x is smaller than epsilon whenever n m are greater than k epsilon. And of course, your x has to be in the set A0. Well, this is an if and only if proof, so there are two directions to prove. We will start by proving that if there's uniform convergence, then the Cauchy criterion here is satisfied. Afterwards, we will show that this is equivalent to uniform convergence. So we assume uniform convergence. Let epsilon be greater than 0, arbitrary epsilon. Since we do have convergence, we know that there's some integer k epsilon, which does not depend on x, such that distance between f at x and fn at x will be less than epsilon over 2, whenever n is greater than k epsilon. In that case, the distance between fm at x and fn at x will be, well, exactly the same as the distance between these things here. Let me just write it down. Right, so I just added 0 in a very specific way. Then I use a triangle inequality. So as long as m and n are greater than this point k epsilon, this will be less than epsilon over 2. This will be less than epsilon over 2, which is epsilon. And so we've shown that the Cauchy criterion holds when convergence is uniform. This is true for every x and a0, because specifically the k epsilon that we've picked did not depend on x. In the other direction, well, if the Cauchy criterion bit is true, then for every x and a0, this sequence of real numbers is a Cauchy sequence. Now we know that in R, Cauchy sequences of real numbers are convergent sequences of real numbers. When I write this, what I'm saying is that the fn at x sequence converges to some number. Perhaps I should be, chi or psi or zeta or what have you, but that specific value depends on what value of x you had, and so I might as well explicitly state the dependence. Fn at x is a sequence of numbers that converges to a number which I call f at x, right? And if I look at the collection of all the x's and their corresponding limit when evaluated through the sequence of functions, this thing here builds a function which I will call f. Okay, but each of those things here is a real number. And so we define f as a function thusly. Okay, so what we have here is that f at n as a sequence converges pointwise to f on a0 using this definition here. Like, all right, so now I have to show that the convergence isn't just pointwise. It is, in fact, uniform. So let epsilon be some positive number. There exists a k epsilon such that fm at x minus fn at x is smaller than epsilon over 2 for all m's greater than k epsilon x is 0. And that's by assumption. Like, we are assuming that this part is true. What we get out of this is that fm at x minus fn at x would be sandwiched between minus epsilon over 2 and epsilon over 2 whenever n and m are greater than k epsilon and x is in a0. So now I'm going to take one of these indices, let's say m, go to infinity. It's true for all n greater than k epsilon and x is 0. And now the strict inequalities become loose inequalities, right? Smaller than or equal to. Minus epsilon over 2 is unaffected by what happens to m. The limit of fm at x exists. We've already shown that to be the case, so we can take it away. It gives us f at x minus fn at x, which is less than epsilon over 2 for all n greater than k epsilon, x is 0. What this means is that f at x minus fn at x is less than or equal to epsilon over 2, which is less than epsilon for all n greater than k epsilon, which I remind you still does not depend on x, right? Whenever n is greater than k epsilon and x is in a0, and this really says that the fn's converge to f, which we've built by looking at the convergence of the Cauchy terms in here on a0, which is what we wanted to show. So in order to show that a sequence of functions converges, you don't need to exhibit the limit, you just need that it is a Cauchy sequence of functions. And then you will have uniform convergence of the actual sequence of functions. Consider the following example. We have a sequence of functions fn which are given by either nx if x varies between 0 and 1 over n, or 2 minus nx if x varies between 1 over n and 2 over n, and 0 otherwise. Here these are functions that I defined in the interval 0, 1, 2r. What do these functions look like? Well, if n is equal to 1, you'd have the function 1 times x between 0 and 1 over 1. So the function x between 0 and 1 over 1, and there's nothing else. These other two branches don't. If n is equal to 2, then you have the function 2 times x between 0 and 1/2, and then 2 minus 2 times x between 1/2 and 2. So you have this one here. If n is equal to 3, this, n is equal to 4, this, and so forth. What do you think this function is going to be going to? Well, pointwise, definitely each of these points will eventually find itself to the right of some 2 over n. And so, as a sequence, we would expect all of these to go to 0. So if there is going to be a limit to the sequence of function, either pointwise or uniform, that limit has to be the identical function 0. Fn will converge to f on 0, 1 pointwise, but Fn does not converge to f uniformly on 0, 1. The fact that it does converge pointwise to f on 0, 1 is easy, right? We'll start by saying cases where x is equal to 0. So when we do pointwise convergence, it makes sense to look at various values of x separately, right? Because our value and epsilon in the convergence definition will depend on the choice of x that we've made. At least could depend on the choice of x. Right? So if x is equal to 0, we know that Fn at x is actually equal to 0 throughout. Right? You're always either in this branch here. If x is 0, you get n times 0, which is 0. And so we definitely get that Fn at x converges to 0. If x is anywhere else in the domain, so greater than 0, but up to 1, potentially including 1, then you can find an integer n such that 2 to the n is smaller than x. You couldn't do so if x was equal to 0, but if x is not 0, by the Archimedean property, this makes sense. You can see 2 over x smaller than n, and then you rearrange the terms. Now what this says is, whenever n is greater than n, then Fn of x is actually equal to 0. You're in this branch here of the function, and so eventually Fn of x converges to 0 as well. So in both of these cases, we definitely have that pointwise the values Fn at x converge to 0, which is the value of the function at the point x. Now intuitively you should look at this and say, but the convergence cannot be uniform, right? As your values of n are increasing, in a sense this function gets squished against the vertical axis. In order to squish this thing so that you eventually get the horizontal function 0, you need to break something. You need to have a discontinuity. Like the continuous intuition you should have is that I keep on pushing something which should come up with, well, right, which should provide me with, well, this should provide me with something here. But that's not what I'm seeing. I'm not seeing that at all, right? Because the limit is actually this function. So something doesn't fit with what you think should happen. You need to break the continuity, if you want, of the process in order to get the pointwise limit. That's an indication that the convergence is probably not uniform. Let's actually show that. So we'll pick an epsilon 0 1/2. I want you to note that the difference between Fn at 1 over n and then f at 1 over n is always going to be, well, what is Fn at 1 over n? You go look at the definition, you'd be replacing x by 1 over n in the first branch or in the second branch. That gives you n times 1 over n, which gives you 1. So what that means is we can never get that Fn at x minus f at x would be smaller than epsilon for every epsilon and for every x in the interval, right? We found here a bunch of x's for which Fn at x minus f at x will be equal to 1. So greater than the epsilon if we pick one of the epsilons to be 1 over 2, say. So we conclude that the convergence, though pointwise, is not uniform.